Welcome back to the final part of our lecture on inheritance. In the previous segments, we explored how inheritance connects classes in a hierarchy, how polymorphism gives them dynamic behavior, and how method overriding lets us specialize functionality. In this segment, we'll go even deeper. First, we'll see how constructors behave in inheritance and how constructor chaining works. Then, we'll introduce a powerful concept: abstract classes. These allow us to define blueprints for future classes, setting structure and enforcing method implementation. By the end of this part, you'll understand not just how to inherit structure, but how to design it for flexibility, safety, and clarity. This slide revisits constructors in a base class. The person class includes both a default constructor and a parameterized one. Why is this important? When a subclass like student inherits from person, it can call either constructor, depending on whether it provides arguments or not. This ties back to the idea of controlled object initialization. We allow flexibility in object creation, but maintain structure through constructor logic. In this example, we define a base class employee and a derived class commission employee. Both classes have constructors, and when we instantiate the child class, the base class constructor is called first. This is the constructor chaining model in C#. Object constructor runs implicitly, then employee constructor runs, then commission employee constructor runs. This ensures that general features are initialized before specialized ones, a vital part of safe inheritance. This program proves what we just said. When we create a commission employee, the console outputs employee constructed, commission employee constructed. This reinforces the top-down nature of constructor calls in inheritance. It's also a good debugging tool. If something goes wrong during initialization, these messages help trace what was run and in what order. Here, the base class employee now requires constructor arguments. So when the child class commission employee is constructed, it must call the base constructor explicitly using :base. This ensures the parent class gets all the data it needs, even when the object is being created by a subclass. This technique is essential in real-world class hierarchies, where base classes often encapsulate critical setup logic. Now we enter a new phase of OOP, abstraction. An abstract class is one that cannot be instantiated. It's designed to act as a base, a general template for other classes. It may contain abstract methods, methods with no body, which must be implemented by derived classes. This concept is perfect when we want to define a contract, but defer the exact behavior to subclasses. This summary ties everything together. Constructors in inheritance run from base to derived. Use :base to pass data to base constructors. Abstract classes enforce structure. They require subclasses to fill in specific behaviors. This bridges our earlier topics: object construction, polymorphism, method overriding, and introduces design by contract through abstraction. Abstract classes capture shared traits, but leave the details open. Think of person as a concept. You never create a generic person in your system, only specific types like student or faculty. So we mark person as abstract, allowing shared structure, while ensuring that only meaningful concrete classes can be instantiated. Key distinction: abstract class cannot be instantiated, used only for inheritance. Concrete class can be used directly to create objects. C# syntax: public abstract class. Person. Abstract classes are a design commitment. You're saying, this class is not complete on its own. You must extend it. Here we highlight the three defining traits of abstract classes. Cannot instantiate directly. Can include abstract methods that must be overridden. Can also contain concrete methods, properties, or constructors. This makes abstract classes both flexible and strict. They provide reusable code, but also demands certain behaviors from all children. This animal class demonstrates how abstraction works in C#. It has a private field for name, a public property to access that name, and an abstract method speak, which forces subclasses to provide an implementation. This is a great example of partial implementation, sharing logic, like the name, while deferring behavior, like the sound an animal makes. Now we implement two concrete classes, dog and cat. Each class calls the base constructor with base, name. Each one overrides speak to return its specific sound. This is classic abstraction plus polymorphism, shared structure through the abstract class, custom behavior through overriding. This is a basic demonstration. We create a dog named Spot and a cat named Puff. We call speak and output their names and sounds. Here, even though we're calling the same method, the behavior depends on the actual class, thanks to polymorphism. This slide is the real power of OOP in action. We pass both dog and cat objects to a method that accepts an animal. Inside, it uses the common speak interface and gets different results depending on the object. This is polymorphism and abstraction working together. The base class defines the method, and each subclass delivers its own response. The main program doesn't care if it's a dog or cat, only that it's an animal that can speak. We end this section with a strong summary. Abstract classes create a common definition for child classes. They can't be instantiated directly, but can contain shared code. Abstract methods define required behaviors, implemented by each subclass. This structure makes polymorphism clean, extensible, and scalable. Think of abstract classes as the template method pattern, part code, part contract. It's the ideal mix of structure and freedom in object-oriented design. That concludes our deep dive into inheritance and abstraction. From basic class extension to constructor chaining, and now to abstract classes and polymorphism, you've now seen how C# allows us to create powerful, safe, and modular class hierarchies. These tools are foundational for any real-world object-oriented system. In our next lecture, we will push further into interfaces, where abstraction becomes even more flexible. Interfaces let you define what should be done, without caring how, and they allow multiple inheritance of behavior. Until then, keep practicing, refactor some of your older code using abstract classes, and start thinking like a software architect. You're no longer just writing programs, you're designing systems.